Vanakkam. Welcome to this course on biomedical instrumentation. We just started looking at sensors and transducers. In this video, we will look at some examples and some characteristics of sensors and transducers. Okay. So, what is the difference between sensors and transducers? This one. What is the difference? This one essentially detects physical or physiological phenomena. Transducers converts energy. Fundamental difference. Always you have, I will be repeating several times. When I repeat something more than 3 times, that means that it is a very, very important principle. Please remember this. Okay. I will repeat this because it is important. So, what is the difference? Physiological transducers are essentially crucial at the input stage of any measurement system, any biomedical measurement system. Physiological transducers are important. For example, this is a arterial line that is useful to measure. For example, this might be used for many things. For example, it might be used in measurement of pressure. It might be used for many different things, or it might actually be used for transfusion. Many different things, right? Important principle of transduction: energy conversion. Important principle is energy conversion. And the characteristics of transducers directly influence and affect the overall performance of the entire measurement system or the measurement instrumentation. What are all the various characteristics? When you say characteristics, what are all the characteristics? When you say characteristics, what do you mean by that? What do you mean by characteristics? Signal to noise ratio, dynamic range, we have already said this, but we will say again. Dynamic range, frequency response, etc. Right. Suppose there is an interpreter or a translator who converts one language that is spoken into a different language. Consider, for example, Prime Minister of India who speaks only Hindi and English is conversing with say the President of Russia, who does not speak Hindi, neither Hindi nor English, only speaks Russian. They will usually have an interpreter or a translator. This person will listen to the Indian Prime Minister in Hindi and then translate to the Russian President in Russian, and then listen to the Russian President in Russian and translate to the Indian Prime Minister in Hindi, for example, or English for that matter, right? Like that, these biological transducers essentially convert the language of biology into the language of electrical engineering. 2 languages. There is no common interface. That common interface happens to be the transducer, right? So, likewise, that's just for the sake of comparison I am saying. So, you want to convert from the biological language to electrical or electronic language. Why electrical? What is big deal about electrical? Because I can then digitize it, transmit it, digitally process it and perform a whole bunch of processing and decision making systems. I can enable so many decision making systems with the electrical system. That is why. Okay. So, what are some of the characteristics of a smart sensor? Right? A smart sensor essentially performs integration. It combines multiple sensing elements with one built-in electronic circuitry. Usually, for example, MEMS based sensing systems, CMOS technology with, that integrates CMOS technology that integrates multiple measurements into single chip. For example, what are the many things that it could do? Amplification, amplify, analog to digital conversion, right? It could also perform temperature compensation, or it could take a calibration signal and then calibrate itself, self-calibration. These are various possibilities, for example, right. Oh, we have that. Essentially perform tasks amplification, analog digital conversion, calibration and temperature compensation directly at the sensor level. Edit this starting with amplification. Okay. So one chip can perform sophisticated functionalities, multiple sophisticated functionalities like amplification, AD conversion, analog to digital conversion, self calibration with an input of a calibration signal and temperature compensation directly at the sensor level, right. This means that external processing will be relatively reduced. It reduces or lessens the workload on external general purpose computers or microprocessor systems. Also, this means that you can reduce the package size or enable miniaturization. So, your device will be really small because many different functionalities are integrated into a single chip, which is why it enables miniaturization. And of course, because there are not many different systems or circuitry, it results in lower power consumption. Power consumption happens to be a critical factor in many measurement systems, but not all, right. And it improves reliability. For example, consider modern smartphones. Modern smartphones have, you know, measurement systems, or smart watches for example have measurement systems that measure blood pressure, that measure whether you are stressed or not, or give an indication of whether you are stressed or not. That measures whether you are sleeping or not, that measure your ECG, that measure whether you are walking or not, and how much you have walked, and what is the pulse rate, so many different, blood oxygenation, saturation level, so many different things, right. Or smart watches. Smartphones are smart watches. Essentially have one or a few chips that could perform multiple measurements, right? Something to keep in mind. What are the ideal applications? Essentially, you are interested in situ or remote monitoring. For example, this sort of, what is this? This is I mean an example of what is being measured here. One needs to understand this. I suppose this is EGG, but one has to check what it is. And then this is EEG, electroencephalograph or brain activity. Right? Many times you are interested in measuring pressure. One method to use to perform pressure measurement is to use piezoresistive effect. You know, piezoelectric effect. What is piezoresistive effect? This is a situation in which a change in the pressure or a change in the force causes a change in the resistivity of a material. How can resistivity of a material change? Because that material is likely a semiconductor material, because of that reason. And usually, for example, if you are interested in measuring force using a strain gauge, usual foil based strain gauges have gauge factor less than 10, but the silicon strain gauges can have gauge factors more than 100. For example, in our lab we have in our brain lab at IIT Madras, we have the ATI nano 6-component force torque sensors that take advantage, that exploit the principle of piezoresistivity to measure forces in 3 directions and moments in about the 3 axes. These are silicon strain gauges whose gauge factor is above 120. An extraordinarily sensitive force measurement system that we use to study fingertip forces in our lab, because we are working in hand and finger function. So ours is one of the only few labs in the world that has an full level 5-finger force measurement system that can measure forces applied by all the 5 fingers on a handheld object. Ours is one of the very few, there are like a handful of labs, excuse the pun, there are a handful of labs that have a full 5 sensor system. Our lab is one of them. Why I am saying this? Because this gauge factor of these silicon strain gauges is more than 100. Biopotential electrodes are specialized sensors that convert electrical activity, that transduce small electrical signals. For example, the EEG signals are in the order of microvolts, whereas your detecting system or display systems usually are in the order of volts. So, you will have to amplify minimum 10,000 times, right. The physiological activity that is happening in the brain will be of the order of microvolts, but you are interested in displaying it in the order of volts, right. ECG order of millivolts, EEG order of microvolts, right. So, obviously the characteristics of the biopotential electrode directly affect the input stage of the amplifier, because you are interested in having high input impedance. Typically a textbook say that high input impedance means more than 10 mega ohms, but practically you are interested in having input impedances of the order of hundreds of giga ohms. This is what you want. Why is this important? Noise characteristics, because you do not want loading, you want to minimize loading. And to reduce noise, what are the various sources of noise? Thermal noise or the so called Johnson noise, thermal noise, 1 over f noise or flicker noise, shot noise. Right. So, when you are amplifying, you are interested in using a system that can have high noise characteristics, and that system usually is the instrumentation amplifier. This is a course on biomedical instrumentation, and I am glad that I am able to introduce the idea of instrumentation amplifier in one of the very first classes. Instrumentation amplifier, why is this important? This is a 2-stage 3 op amp system that has high CMRR. What is CMRR? Basic electrical engineering, or from your basic op amp course, you know what is CMRR. CMRR means common mode rejection ratio, right? Not. For example, another example of having a or actively cancelling noise is driven right leg system in ECG. This is similar to noise cancelling headphones. How does noise cancelling headphone work? Essentially, there is a microphone that detects noise, ambient noise, and then as feedback, negative feedback, it sends that amplified version of that noise, ambient noise, along with the music that is being heard. That way, whatever noise is outside is not heard by on the headphone. Only the music or the audio that the person is intending to listen is heard. Right? This is the principle of noise cancelling headphone. Likewise, right? This is similar to driven right leg system in ECG, similar to like noise cancelling or active noise cancelling. Something to keep in mind, right? Or you are interested in converting acoustic signals to electrical signals. In a traditional, for example, stethoscope, this essentially transmits heart or lung sounds directly as acoustic vibrations, right? Or if you use a digital stethoscope, this may use a microphone that then converts this into an analog signal and then digitizes it. It may digitize it, it may not digitize it. But a microphone in an electronic stethoscope essentially converts the sound vibrations into electrical signals. essentially a repetition, that, right. And these electrical signals are then amplified, and this amplification essentially detection of sounds that are too low, having very low intensity to be perceived by the human ear. It also allows the detection of sounds that can otherwise not be heard by the human ear, right. So, infrasonics, there are indeed some physiologically crucial signals that are present at the low end of the frequency spectrum that the human ear cannot perceive. These are called some specific heart murmurs. We will discuss that when we discuss phonocardiogram in one of the future weeks. We discuss phonocardiograms. In that week, we will discuss the details of what this is. Right? So, there are indeed such cases. So, with this we come to the end of this week. In this week, we looked at end of this, edit this. With this, we come to the end of this video. In this video, we looked at some examples and characteristics of sensors and transducers. Essentially, we emphasize system integration. This is going to be a recurring theme in this course. Throughout, I am going to keep on saying that system integration, system thinking. That you need to integrate information from multiple sources, system integration, principles of physics and physiology, physics, physiology, principles, right. Management of noise, or minimization of noise, more specifically noise minimization, right. And critically, active signal conditioning, right. You are interested in miniature, smart, electrically safe medical devices. This is what you are interested in. Critically, what are the things that I want you to take home from this class? What are the key takeaways? Sensors are not transducers. All crows are black, but all black things are not crows. All sensors are transducers, but all transducers are not sensors, right. Impedance matching is crucial. And there is such a thing called as noise floor, below which you really cannot reduce the noise. That means amplification sometimes can also result in noise amplification, sometimes may also amplify noise. This is important. It may not always improve SNR. Do not assume simply amplifying will improve signal to noise ratio. Sometimes you may end up amplifying noise, which may actually be counterproductive. It might reduce the signal to noise ratio if you have already reached your noise floor. Something to keep in mind. There is such a thing called as minimal noise. Below this, you really cannot physically and physiologically reduce the noise. Biocompatibility. And digital conversion sometimes can helps in better measurement and transmission. So, with this we come to the end of this video. Thank you very much for your attention.